Alright, so now that we have our points, we are going to want to fit the data, and we're going to want to do that with a linear regression and by minimizing the sum square deviation. So first we're going to start with the linear regression. This is involving a lot of matrix math, but basically we have the equation in the way in the format that we want it. So it's the Sherwood number, which is equal to some constant A times the Reynolds number to some power B times the Schmidt number to some power C. And we're trying to figure out what the A, B, and C values are. So we're gonna do manipulate some matrices to actually get a good guess of what those values are. So to do this, we need to isolate those variables, or our unknowns, and put them in a matrix all on their own. So first we're going to want our design column, or our design matrix, sorry. And to do this, we're going to need an extra column in there that is full of ones, that is full of the Sherwood number. That way we can get the actual values for our unknowns. So we're going to make our matrix like this. So we're going to need to use NumPy again. Sorry about that noise in the background. Okay, good, it's done. Never mind. It's going to be equal to np.column stack np.column stack, and so this is where we're actually going to be making our matrix. And so, like I said before, we're going to need our ones column. So, sorry. Okay, so we're gonna need ones that are in the column as many numbers as the Sherwood number will have. So we're gonna np.ones like, and it's gonna be like the Sherwood number. And then we're gonna need the natural log. So we're gonna do the np.natural log of the Reynolds number, and then we're going to need the natural log of the numbers in the Schmidt number, and that makes our thing. So I did something wrong. NP has no, forgot an S there. Ones like cannot extract the type from, here we go. Invalid syntax, and I just have an extra parentheses there. Alright, there we go. Okay, got it figured out. So now we have that, we need to set up a matrix for our unknowns. And so for unknowns, we're just going to call it U. So U is equal to, we're going to have to do some inversions of matrices, because we're going to be doing, we're going to have our design matrix with the ones, the natural log of the Reynolds number, and the natural logs of the Schmidt number, and we're going to multiply it by the matrix of our unknowns, which is the natural logs of A, B, and C, and then that should equal the matrix of the natural log of the Sherwood number. But then we're trying to isolate the unknowns matrix, because that's what we're trying to find. So we're going to have to multiply by the transposed matrix of the transposed design matrix, and then divide both sides, because when we multiply by the transposed, we get the transposed matrix times the regular design matrix times the unknown matrix. Divide both sides by the multiply both sides by the design matrix times the transpose design matrix, and take the inverse. So we're doing the inverse, which is dividing by. And that's how we're going to get our unknown matrix by itself. So to do that, we're going to have to make our inverse. So NP, we're going to do the linear algebra like we did before, and do the inverse of the design matrix. But we have to do it the transposed design matrix. All right, and then we're going to multiply it just by the regular design matrix. All right, and then we're going to have to go outside the inversion and just do the we'll multiply this by the design matrix, the transposed design matrix times, that should be a @ symbol for matrix multiplication. I delete the T, and the design matrix. Okay, and so we're almost there. We just have to multiply by the natural log of our Sherwood number. And that should give us U. Did something wrong. Give me just 1 second to find it.